In January of 2022, a team of physicists encoded a single piece of quantum information into one end of a quantum processor, fired a carefully timed pulse through the system, and watched it appear on the other side. The information had not been copied. It had not traveled through any wire. The 9 tiny superconducting circuits sitting inside a refrigerator cooled to 1/100th of a degree above. Absolute zero had done something that looked, by a very specific and deliberate mathematical interpretation, like sending that information through a wormhole. That is not a metaphor. That was the actual claim. Some quantum systems, when you look at them through the right mathematical lens, are not merely similar to gravitational systems. They are identical to them. Not approximately. Not in certain limits. Exactly. Mathematically, interchangeably identical. You can write down the equations describing a cloud of particles doing quantum mechanical things in flat space, and by a precise transformation, those exact same equations describe a black hole sitting in curved spacetime in a higher dimension. Same physics, different description, 2 faces of one reality. Physicists call this holography. The term comes from the way a hologram encodes 3-dimensional information on a 2-dimensional surface. In this case, the idea is that all the information describing what happens inside a region of curved spacetime, including everything inside a black hole, can, in principle, be encoded on the boundary of that region in a lower dimensional quantum system without gravity. The 2 descriptions aren't analogies. They're the same equations. The foundational results behind this idea was worked out in the late 1990s by the Argentine-American physicist Juan Maldacena. He showed that a particular kind of quantum field theory in flat space, defined on the boundary of a region, is precisely equivalent to a theory of gravity inside that region. The result is called the ADS-CFT correspondence, where ADS stands for anti-de Sitter space, a particular type of curved spacetime, and CFT stands for conformal field theory, a type of quantum field theory with special mathematical symmetries. Maldacena's paper has been cited tens of thousands of times. It is one of the most influential results in theoretical physics of the last 3 decades. What it means in practice is this: if you build the right kind of quantum system in a lab, and you look at it through the holographic lens, you might not just be studying quantum information. You might be studying gravity. That idea is what made the 2022 experiment possible. The quantum system at the heart of the experiment is called the SYK model. The name comes from the initials of 3 physicists, Sabir, Sachdev, Ginwoo V, and Alexia Katav. Sachdev and they originally proposed the model in the 1990s to study certain strange metallic systems. Katav later reformulated it and pointed out something that made it immediately interesting to anyone thinking about holography. The SYK model describes a collection of particles called Majorana fermions, all interacting with each other in a particular random pattern. Every particle interacts with every other particle. The strengths of those interactions are chosen randomly, drawn from a distribution. The result is a system with no obvious structure, no lattice, no preferred geometry. Just a cloud of particles, all talking to each other in a maximally chaotic way. That chaos is precisely the point. In 2016, Maldacena, along with Douglas Stanford and Stephen Shea, proved a result about quantum chaos that drew a sharp line around the SYK model. They showed that all quantum systems obey a strict upper limit on how fast information can scramble through them. Think of scrambling as the process by which a localized piece of information, something that exists at a specific place in a system, gets spread out and mixed into the global state of the system until you can no longer find it just by looking locally. It's the quantum version of what happens when you drop a drop of dye into a glass of water. At first the color sits in one spot, then it spreads. Eventually, the whole glass is uniformly tinted, and there's no way to find the original drop just by looking. The rate of scrambling, it turns out, has a speed limit. That limit depends on temperature and on Planck's constant, the fundamental quantum of action. No quantum system can scramble faster than this limit allows. Black holes, when you work out their quantum properties carefully, hit that limit exactly. They are the fastest scramblers in nature. And so does the SYK model. That's not a coincidence. It's the signature of the gravitational duality. A system that scrambles at the maximum possible rate is, through the holographic lens, mathematically identical to a black hole. This is the result that told physicists the SYK model might actually be useful as a laboratory stand-in for gravitational physics. Not a toy, not an analogy, a precise duel. But there was a problem with actually running the SYK model in a lab. The full version of the model requires a large number of fermions all talking to each other. The number of interaction terms grows rapidly with the size of the system. To get clean gravitational behavior to emerge, you need hundreds of particles interacting through hundreds of coupling terms. No quantum computer that existed in 2022 could run that. Not Google's Sycamore. Not anything. If you wanted to study SYK physics on real hardware, you had to find a way to make the model smaller without breaking the properties that made it interesting. That's where the machine learning came in. The team used a learning algorithm to prune the SYK model. They started with the full model, then systematically removed interaction terms, keeping only the ones that the algorithm identified as essential to preserving the gravitational behavior. The goal was to find the smallest possible version of the model, using the fewest interaction terms and the fewest particles, that still exhibited the key signatures of holographic duality. The process produced what the team called a sparsified SYK model. 7 major, a small number of interaction terms, small enough to fit on 9 qubits of Google's Sycamore processor. The team then argued that this stripped-down version was still gravitationally faithful, that it still sat through the holographic lens on the gravitational side of the duality, that the machine learning had found a shortcut through the model space without stepping off the holographic map. That argument, which seemed reasonable when the paper was published, would later become the sharpest point of contention. The experiment itself drew on a theoretical result that Daniel Jeffreys had worked out years earlier. In a 2016 paper written with Ping Gao and Aaron Wall, Jeffreys showed something striking. If you have 2 quantum systems that are entangled with each other, you can couple them together in a very specific way. That coupling, on the gravitational side of the holographic dictionary, looks like a burst of negative energy passing between 2 black holes. And negative energy is precisely what general relativity says you need to prop open a wormhole. Without that pulse, a wormhole in general relativity pinches shut almost instantaneously. The throat collapses. Nothing can pass through. With the negative energy pulse, the throat stays open just long enough for something to slip through before it closes again. The Gauge-Ferris wall mechanism, as physicists came to call it, gave a concrete recipe for what a traversable wormhole would look like through the holographic lens. It wasn't a recipe for building a real wormhole in actual spacetime. It was a recipe for running a quantum system that, when viewed through the holographic dictionary, behaved as if a wormhole had briefly connected to black holes. That's what the team tried to build. The Sycamore processor has 53 superconducting qubits in total. For this experiment, 9 of them were doing the work. They were configured as 2 copies of the sparsified SYK model, one representing each side of a holographic universe with a black hole in it. The two sides were entangled with each other. Then the coupling pulse was applied, the experimental stand-in for the negative energy shockwave. Then the team waited, and then they saw the signal. A qubit of information had been encoded into one side of the system. After the pulse, it appeared on the other side, not copied, moved. In the language of quantum information, that's teleportation. Qubits had been teleported before. That part was well established. What was new was the interpretation. The team was arguing that this particular teleportation had happened not because of the standard quantum teleportation mechanism, but because the information had fallen into a black hole on one side, passed through the throat of a wormhole, and emerged from a second black hole on the other. They listed 5 specific features of the signal that they argued were gravitational fingerprints, things that a simple teleportation experiment wouldn't show, but that a genuine traversable wormhole would. First, the information scrambled and thermalized the way it would if it had fallen into a black hole. Second, the signal appeared with a small delay, the kind general relativity predicts for something crossing a region of curved spacetime. Third, the signals from the two sides came out in the right causal order. Fourth, a pattern in the data the team called perfect size winding, which they described as the smoking gun, a signature specific to gravitational teleportation. Fifth, the coupling between the two sides matched the behavior expected from a negative energy shockwave. 5 fingerprints, all pointing at gravity. If the team was right, this was the first time in history that a controlled laboratory experiment had produced a piece of genuine gravitational physics, not by building a black hole. Nobody had done that, but by building something that, through the precise mathematical correspondence of holography, was the same thing as a black hole and a wormhole, just viewed from the other side. The result landed on the cover of Nature on the 1st of December 2022. The New York Times covered it. So did The Guardian, New Scientist, and Quanta magazine. The Caltech press release called it a first-of-its-kind quantum gravity experiment on a chip. For a few weeks, the field felt like it had finally dragged gravity into the laboratory. Then, on the 15th of February 2023, 3 physicists at the University of California, Berkeley, uploaded a paper to the preprint server Arxiv that nobody at Caltech, Harvard, or Google wanted to read. Their names were Bryce Cobrin, Thomas Schuster, and Norman Yao. They were not outsiders. Yao runs a research group at Berkeley that works precisely at the intersection of quantum information and gravitational physics. When the Nature paper came out, Yao and his colleagues did what careful physicists do. They sat down and worked through the mathematics to understand how something as small as a 7 fermion model could possibly be doing what the headline said it was doing. What they found was a fundamental problem with the Hamiltonian, the stripped-down SYK model that the machine learning algorithm had produced had a specific mathematical property. Its interaction terms all commuted with each other. In operator language, 2 operations commute if the order in which you apply them doesn't matter. If a times b equals b times a, they commute. This sounds technical, but its physical consequences are severe. To understand why, think about what scrambling and thermalization actually look like at the level of quantum operators. A system thermalizes when its different parts interact in a chaotic, non-commuting way. The operators don't commute. Applying one operation first versus second gives you a different result. The system's components get tangled up together in an irreducible way. Information that starts in one part of the system gets distributed across all the others because the parts genuinely interfere with each other. A system whose operators all commute doesn't do that. The parts don't interfere. They each evolve independently, in parallel, without genuinely mixing. It's like the difference between a room full of people having a chaotic conversation where everyone is interrupting and responding to each other, versus a room full of people, each wearing headphones, listening to their own separate recording. They're in the same room. They're all doing things at the same time, but none of them is actually responding to any other. The information in one person's headphones never makes it into anyone else's experience. A fully commuting Hamiltonian is the quantum equivalent of the headphones room. And that creates three specific problems for the gravitational interpretation. The first problem was thermalization. The Jafferis team had listed scrambling and thermalization as one of the 5 gravitational fingerprints their experiment had shown. But a commuting Hamiltonian cannot thermalize. Not really. The mathematical requirement for true thermalization is precisely the kind of non-commuting, chaotic dynamics that a commuting system can't produce. So the Berkeley group argued that the first fingerprint was not actually present in the experiment. It only appeared to be. The second problem was the smoking gun. Perfect size, winding. This was the signature that Jafferis' team had singled out as the most distinctive evidence for a gravitational interpretation. Kobrin, Schuster, and Yau showed that perfect size, winding, is not specific to gravity. It is a generic feature of small, commuting quantum systems. It shows up in those systems all the time, for purely algebraic reasons that have nothing to do with holography or black holes or wormholes. The signature the team had built the most important piece of their case on turned out to be a mathematical artifact of the simplification. The machine learning algorithm had produced a model small enough to run on a quantum chip, and that smallness and commutativity were what generated the pattern in the data, not gravity. This is a version of a mistake physicists sometimes call the lamppost problem. You're looking for something. You simplify your system until you can actually analyze it, and then the simplification itself produces the pattern you were looking for. Because the pattern wasn't a signal from the thing you were trying to study. It was a shadow cast by the simplification process. The third problem was the teleportation signal itself. When the Berkeley group looked carefully at the shape of the signal, not just whether it appeared, but how it evolved in time, it didn't match what you would expect from a qubit crossing a traversable wormhole in a genuine gravitational system. The shape was wrong. The dynamics were inconsistent with what general relativity would predict for information traveling through a real wormhole. Throat. 3 of the 5 gravitational fingerprints were either absent or explained by properties of the simplification rather than by gravity. The reaction in the field was quiet but unmistakable. John Preskill, a theoretical physicist at Caltech who had not been part of either group, told Quantum magazine that he felt the evidence for a gravitational interpretation was weakening. Vincent Su, a physicist at Berkeley who works on exactly this area, put the sharpest version of the question on the table. Is quantum gravity in the lab dead? Nobody had a clean answer. The Jafferis team did not concede. They published a response arguing that even a commuting Hamiltonian can capture something meaningful. That even if the model wasn't fully gravitational, it wasn't nothing either. Ping Gao, one of Jafferis's longtime collaborators, wrote a separate paper proposing that what the experiment had shown was a kind of pseudo-holographic behavior. Not exactly gravity in the full sense, but not a random quantum system either. A regime where a specific teleportation mechanism operates, distinct from standard quantum teleportation, but also distinct from genuine traversable wormhole dynamics. Something in between. The dispute sat in the preprint literature, unresolved for more than 2 years. Then, in July 2025, Nature did something it doesn't do often. It published the Berkeley critique as a formal peer-reviewed paper in its Matters Arising section, alongside a reply from the Jafferis team. Matters Arising is Nature's mechanism for publishing formal scientific commentary on previous results. It's the journal saying, "This criticism is serious enough to become part of the permanent record. The original paper was not retracted. It remains in the literature. But attached to it now is a formal statement from 3 other physicists saying that 2 of the 5 gravitational fingerprints were not actually present in the experiment, and that the 3rd was generated by the simplification rather than by gravity. The Jafferis team's reply, also published, acknowledged that many of the processes running on the learned Hamiltonian don't have a gravitational description. They maintained that some of them still do. So where does that leave the experiment? The qubit was that part is real. The data is the data. But whether what happened on those 9 qubits had anything to do with a wormhole in the sense the headline said it did is now, as of 2026, an open question with serious doubt attached. The most honest summary anyone in the field gives is that the experiment showed something interesting. Whether that something was genuinely gravitational or just a clever and somewhat misleading toy model has not been settled. And while that argument was still developing, someone else was running a much larger experiment aimed at a much more unsettling piece of physics. 5,564 qubits. That's the number to keep in mind for this next part. The wormhole experiment used 9. This one used 5,564. They used different hardware and they were trying to simulate a completely different physical system. But the contrast in scale is striking. And the question they were trying to answer is one that physicists have been sitting with uncomfortably since the 1970s. The paper appeared in Nature Physics on the 4th of February 2025. The team was led by physicists at the University of Leeds, the Jülich Supercomputing Center in Germany, and the Institute of Science and Technology, Austria. The machine they used was a D-wave quantum annealer connected to the Jülich Supercomputing Center's systems, a different architecture than a gate-based quantum computer like Sycamore, a different approach to quantum computation. And the question they were asking was, what does the end of the universe look like? The scenario they were modeling comes from work done by the physicist Sidney Coleman in the late 1970s. Coleman was working on a question that sounds deceptively simple. Is the universe stable? The naive answer is yes, obviously. The universe has been here for roughly 13.8 billion years. Galaxies form, stars burn, atoms hold together. Everything seems to be working. But stable in the everyday sense and stable in the precise sense that physicists use are not the same thing in physics. A stable state is one that sits at the lowest possible energy configuration. If you push a ball sitting at the bottom of a valley, it rolls back down. It's in a true minimum. But systems can also get trapped in local minima, false vacuums. Imagine a ball sitting in a small depression partway up a hill. It's stable in the local sense. Small pushes and it comes back. But the global minimum, the true lowest energy state, is further down the hill. If the ball gets enough of a push, it will leave the small depression, roll down the hill, and settle into the deeper valley. That's a lower energy state, a true vacuum. Coleman showed that the same logic applies to the quantum fields that fill all of space. The vacuum of the universe. The ground state of quantum fields, like the Higgs field and the electromagnetic field, might not be in its lowest possible energy configuration. It might be sitting in a false vacuum, a local minimum that looks stable from the inside, but that quantum mechanics would allow to tunnel out of if enough time passed. The tunneling process would work like this. Somewhere in space, completely randomly, a small region would spontaneously fluctuate into the true vacuum state. A bubble of true vacuum would nuke. Inside that bubble, the fundamental constants of physics could be different. The masses of particles could change. The strengths of forces could change. Atoms might not hold together in any recognizable form. Chemistry would stop working, and the bubble would expand at the speed of light. converting false vacuum to true vacuum as it grew. You would not be able to see it coming. The edge of the bubble would be traveling at the speed of light, the same speed as the light that would carry news of its approach. The two signals would arrive simultaneously. This is not science fiction. It's a live question in theoretical physics. Measurements of the Higgs boson mass at the Large Hadron Collider, combined with careful measurements of the mass of the top quark, place the electroweak vacuum of the Standard Model in a region that physicists describe as not definitively stable, not definitively unstable, sitting uncomfortably close to the boundary between the two, with significant uncertainties on both sides. Coleman's original calculations suggested that the tunneling rate, the probability per unit volume per unit time that any given patch of space would spontaneously nucleate a bubble of true vacuum, was extraordinarily small. So small that the expected time before such an event would happen anywhere in our observable universe is vastly longer than the current age of the universe. But those calculations carry enormous uncertainties, and nobody had ever actually watched the mechanism happen, even in a controlled model. That's what the Leeds, Jülich, and Eister teams set out to do. They arranged their 5,564 superconducting flux qubits in a circular ring and configured them to behave like a quantum Ising model, a well-understood model in condensed matter physics that can be tuned to mimic many different physical systems. By choosing the right parameters, they set the entire ring up to behave like a one-dimensional slice of a false vacuum, a simplified version of the problem that captures the essential physics of bubble nucleation and expansion without requiring a full three-dimensional simulation. Then they applied an external field that destabilized the false vacuum, analogous to increasing the tunneling probability, and they watched. Bubbles formed. Quantized regions of the ring flipped into a different state, the true vacuum configuration. Small bubbles nucleated first, then larger ones. Some bubbles stabilized, some collapsed, some grew. The team could observe coherent bubble structures containing the equivalent of 300 spin flips across 300 qubits, all changing state together in a synchronized quantum state. The bubbles expanded within the ring. They interacted with each other. They collided and merged. The entire dynamics played out coherently for more than 1 microsecond. 1 microsecond sounds very short, but for a quantum system of this size and complexity, it's a remarkably long time. It corresponds to more than 1,000 of the fundamental time units that the qubit's dynamics operate on. Long enough to study the shape of bubble nucleation, measure the distribution of bubble sizes, track the growth rates, and compare the results against the theoretical predictions of quantum field theory in one dimension. The match was good. The bubbles formed where and how the theory said they would. The dynamics evolved as expected. The size distributions followed the predicted patterns. Nobody challenged this experiment the way the wormhole experiment was challenged. The physics is more conventional. The Ising model is extremely well understood. The behavior of the qubits matched the equations in a straightforward way that didn't require any controversial interpretive steps. The experiment did what it said it did. But sitting underneath both of these stories, underneath the contested wormhole and the uncontested vacuum bubble, is a question that the wormhole controversy forced into the open and that the field has not yet answered. How do you know when a quantum simulation is showing you the truth? For most of the history of experimental physics, the answer was simple and robust. You did the experiment, then someone else did the experiment. If two independent labs got the same result, using different equipment and different methods, the result was probably real. If they got different results, somebody had made an error and the field went looking for it. That rule worked for particle accelerators. It worked for telescopes. It worked for chemistry and materials, science, and almost anything, where you could build a second copy of the apparatus and try again. It is starting to break down for quantum simulation. The whole reason you use a quantum computer to simulate a physical system is because a classical computer can't do the same simulation efficiently. If a regular computer could simulate 100 Fermion SYK model or false vacuum decay in a system of 5,000 interacting qubits, you wouldn't need quantum hardware. You'd just run it on a laptop. The quantum computer earns its place precisely in the regime where classical hardware fails. But that creates a troubling situation. If your quantum simulation produces a surprising result about a wormhole or about how vacuum bubbles form, how do you verify whether the answer is right? You can't simply run the same calculation on a classical computer. That was the problem you were trying to solve by using quantum hardware in the first place. This is the verification problem. It's been quietly present in the field for years, acknowledged in papers, mentioned at conferences, noted in review articles. The wormhole controversy brought it into the open in a way that was impossible to ignore at its core. The problem connects to a deep question in computational complexity theory. Quantum computers are believed to be able to solve certain problems exponentially faster than any classical computer. But verifying that a quantum computer has produced the correct answer can be just as hard as solving the problem classically in the first place. The same computational power that makes quantum simulation valuable also makes quantum simulation difficult to certify. There are tools that help check specific aspects of a quantum device's performance. Cross-entropy benchmarking can measure how well a device is producing the expected distribution of outputs. Shadow tomography provides a way to estimate many properties of a quantum state from a limited number of measurements. Randomized benchmarking helps characterize the error rates of individual gates. These are all useful, but none of them provides a general, reliable way to certify that an arbitrary quantum simulation is producing results that faithfully reflect the physical system. It's supposed to be modeling. Think about what the Berkeley group actually did. They didn't run the experiment again. They didn't build their own version of the wormhole circuit and compare results. They took the mathematics that the original team had used, read it carefully, and found that the model wasn't doing what the team thought it was. The check was theoretical. 3 physicists with pencils and paper working through the implications of a Hamiltonian and discovering that 2 of the 5 gravitational fingerprints weren't there, and third was a mathematical artifact. That is the kind of issue that peer review is supposed to catch before publication. In this case, it surfaced publicly more than 2 years after the paper had been on the cover of Nature. The field moved faster than the checking caught up. In late 2025, a team at Swinburne University in Australia, led by Alexander, reported a new technique for validating the outputs of a certain kind of quantum machine. The machines they were working with are called Gaussian boson samplers, specialized photonic quantum computers designed to perform one particular calculation that is believed to be hard for classical computers. When the Swinburne team applied their new validation method to a previous landmark experiment in Gaussian boson sampling, they found errors, unexpected ones, errors that no one had spotted before, in a result that had been celebrated as a milestone achievement in the field. The Swinburne result doesn't say anything directly about the wormhole experiment or about the false vacuum simulation. Different machine, different problem, but it points at the same nerve. Quantum computers are now doing things we can't independently check. And when we develop the tools to check them, we keep finding that the picture is messier than the headlines suggested. There is something structurally familiar about this pattern. It echoes the early history of computational simulation in other fields. Climate modeling went through a version of this. where increasingly powerful simulations outpaced the tools for validating them. Protein folding predictions went through it. Economic forecasting went through it. In each case, the tools advanced faster than the methods for checking them, and it took years to clearly distinguish between the model produced an output and the model told us something true about the real world. Quantum simulation may be in its own version of that reckoning now. The path through this uncertainty is not a mystery. The field knows roughly what's needed. Tighter mathematical guarantees about the fidelity of simplified models to the systems they're meant to represent. Better validation tools that can certify not just that a quantum device is operating within its hardware specifications, but that the simulation it's running is actually a faithful representation of the physical system it's claiming to model. Cultural pressure to publish not just striking results, but the full diagnostic picture of each experiment, including the limitations of the simplifications used, the range of parameter space actually explored, and the checks that were and weren't performed. The false vacuum simulation at Jülich is solid work. The bubbles formed. The dynamics matched the theory. The path to a three-dimensional version of the experiment is real, and researchers are working toward it. What the SYK model and the holographic program have shown, despite the controversy, is that the conceptual bridge between quantum information and gravity is not merely a theoretical construction. It's becoming something you can probe in a laboratory, imperfectly and with great difficulty, but probe nonetheless. The question at the core of holography, whether spacetime itself emerges from quantum entanglement, is no longer purely a paper and pencil question. It's starting to be the kind of question you can build an experiment around. That's genuinely new, but the Sycamore experiment taught the field something that the excitement of the moment nearly obscured. A teleportation signal is not a wormhole, even if the mathematics allows you to interpret it as one. A pattern in the data is not a gravitational fingerprint, just because you've called it one. A 9-qubit experiment running for a few seconds on a chip in California is not a confirmation that spacetime emerges from quantum information. No matter how many people would like it to be, the deeper questions remain exactly as open as they were before. We don't know whether the spacetime we inhabit is holographic in the full technical sense that the mathematics sometimes suggests. We don't know whether our universe is sitting in a metastable false vacuum, with the constants of physics balanced on a knife's edge that quantum mechanics might eventually tip. We don't know whether the next generation of quantum simulations, running on machines with thousands or millions of qubits, will produce results that genuinely illuminate those questions, or whether they'll produce results that look like answers, until someone reads the mathematics carefully enough to find the artifact hiding inside. What we do know is that somewhere in Santa Barbara, a dilution refrigerator is humming with 9 qubits inside it. Somewhere in Jülich, a different machine is running with 5,564 qubits inside it. Somewhere in Boston and Sydney and Delft and Zurich and Beijing and dozens of other places, physicists are configuring quantum systems to ask questions about gravity and vacuum stability and the deep structure of spacetime that had never been asked in a laboratory before. The answers are not always reliable yet. The tools for checking them are catching up slowly. The culture of the field is adjusting to a new regime where the machinery has outrun the methods, but the questions themselves are real. The tension between quantum mechanics and gravity, the two most successful theories in physics, which cannot both be right in their current forms, is the deepest open problem in fundamental physics. The holographic program is one of the most serious attempts to resolve it. The quantum simulation program is one of the few ways to test that resolution in something resembling a controlled experiment. Both of those things are true. The controversy is also true. The verification problem is also true. None of them cancels any of the others. The field is learning to work in a new regime, one where results come faster than they can be fully checked, one where the most important experiments are also the hardest to verify, one where the gap between what the mathematics says and what the experiment actually showed has to be navigated with more care than the press release suggests. That adjustment is happening right now. The next few years of experiments will not settle whether spacetime is holographic. They probably won't settle the question of false vacuum stability either, but they'll push the boundary of what can be asked in a laboratory, and they'll sharpen the tools for knowing when the answers are real, if you want to watch that process happen in real time, with all the argument and uncertainty that comes with genuinely open questions. The work is available. Most of it ends up on Arxiv before it ever appears in a journal. The full back and forth of the wormhole debate is there, from the original Nature paper through the Berkeley critique to the formal matters arising exchange. The false vacuum paper is there. The Swinburne validation work is there. Physics at this frontier is slow and careful and sometimes brutally corrective, but it is also one of the few human activities where the questions are this large and the tools for answering them are improving this quickly. We are learning to listen with new instruments, knowing that some of what we hear will be echo and some will be signal, and working with increasing rigor to tell the difference, to understand why the wormhole experiment landed with such force. You need to understand what had been building in theoretical physics for more than 2 decades. The holographic principle didn't arrive out of nowhere. It emerged from a series of increasingly uncomfortable encounters between general relativity and quantum mechanics. 2 theories that each work extraordinarily well inside their own domain and that refuse, stubbornly and persistently, to be reconciled into a single coherent framework. General relativity describes gravity. It describes how mass and energy curve the fabric of spacetime, and how that curvature tells matter how to move. It governs the orbits of planets, the behavior of black holes, the expansion of the universe itself. Its predictions have been tested to remarkable precision. Gravitational waves, detected for the first time in 2015 and attributed to the merger of 2 black holes over 1 billion light-years away, matched the predictions of general relativity to extraordinary accuracy. The theory works. Quantum mechanics describes everything else. It describes how particles behave at the smallest scales, how atoms interact, how light is emitted and absorbed, how chemical bonds form. It underlies every semiconductor, every laser, every nuclear reaction. Its predictions are the most precisely verified in all of science. The magnetic moment of the electron, a quantity related to how strongly the electron acts as a tiny magnet, has been measured and calculated to more than 10 decimal places, and the measurement and calculation agree. The theory works, but when you try to combine them, when you try to apply quantum mechanics to the gravitational field, everything falls apart. The calculation produces answers that are infinite, not very large, actually infinite. The standard technique for dealing with infinities in quantum field theory, which is called renormalization, fails for gravity. The theory is what physicists call non-renormalizable. The infinities can't be tamed. This is not a minor technical problem. It means that our 2 best theories of how the universe works are mutually incompatible. At some fundamental level, one of them is wrong, or both of them are incomplete, or both of them are approximations to something deeper that we haven't found yet. This is the central open problem of theoretical physics, the holographic principle, and the ADS-CFT correspondence that Maldacena discovered is the closest thing the field has to a resolution. It doesn't solve the incompatibility directly. It doesn't give you a single unified theory of quantum gravity that smoothly reduces to general relativity in one limit and quantum mechanics in another. What it gives you is a precise mathematical dictionary between a quantum theory without gravity and a gravitational theory in one higher dimension. It says, these two things are the same. That's not the same as unification. But it's something. It means you can, in principle, take a question about gravity and translate it into a question about quantum mechanics. The quantum mechanics might be tractable when the gravity wasn't. Conversely, you can take a question about quantum systems and translate it into a gravitational question. The geometry might give you intuitions that the quantum calculation hid. This dictionary has been enormously productive in theoretical physics. It's been used to study strongly coupled quantum systems in condensed matter physics, quark gluon plasmas produced in heavy-ion collisions, and the behavior of black holes. In many of these applications, the gravitational side of the correspondence provides an easier calculation than the quantum side, or vice versa. Physicists choose the description that's easier to work with for the problem at hand, but there's always been a question hanging over all of this. Does the holographic correspondence describe our actual universe? The original ADS CFT correspondence was worked out for a specific type of spacetime, called anti-de Sitter space, which has a negative cosmological constant. Our actual universe appears to have a positive cosmological constant. It's described not by anti-de Sitter space, but by de Sitter space, which is different in important ways. Whether the holographic principle applies to de Sitter space, whether there's a precise version of a DSCFT that describes our actual universe, is a major unsolved problem. So the holographic program lives in a complicated epistemic situation. It's extremely powerful as a mathematical tool. It's almost certainly telling us something deep about the relationship between quantum mechanics and gravity. But whether it's literally true of the universe we live in, or whether it's a precise mathematical duality that applies to a different kind of space-time than the one we inhabit, is unclear. The wormhole experiment was an attempt to make this abstract correspondence concrete, to build something in a laboratory that would force the holographic dictionary to make a specific, testable prediction. If the experiment worked as advertised, it would mean that the holographic dictionary was not just a mathematical tool, but a physical reality that could be probed in the lab. That's why the stakes felt so high, and that's why the Berkeley critique, when it came, felt so deflating to some parts of the field. Not because anyone had discovered that holography was wrong. The mathematical correspondence is still solid. The SYK model is still dual to a gravitational system in the appropriate limits. The Gauge-Friis wall mechanism is still a valid theoretical result. None of that changed. What changed was the claim that this particular experiment, on this particular stripped-down model, had actually crossed the line from quantum information into gravity. It hadn't, at least not clearly. The sparsification process, the machine learning step that had made the whole experiment possible by fitting the model onto 9 qubits, had produced a model that looked gravitational in some ways, but was commuting in a way that real gravitational systems aren't. The simplification had cut out the very thing that made the gravitational behavior genuine. That is an uncomfortable lesson. It's not a lesson about whether holography is real. It's a lesson about the gap between a system that is holographically dual to gravity and a system that merely resembles such a system in some respects. The gap can be invisible in simplified models, and in quantum simulation, simplified models are all you have. This connects to a much older problem in experimental physics, one that gets less attention than it deserves: the problem of model validity. Every experiment involves a model. You don't measure nature directly. You measure a physical system that you've built or found. You apply a theoretical framework to interpret the measurement, and you report a result. The result is only as good as the combination of the measurement and the theoretical framework. If the framework has a flaw, the result inherits that flaw. This is true in every field of experimental science. In most experiments, the theoretical framework is well established, and the main uncertainty is in the measurement. You know what you're measuring. You just need to measure it precisely. But in quantum simulation, both sides of this equation have large uncertainties simultaneously. The hardware is noisy. The qubits make errors. The gates aren't perfect. And the theoretical model being simulated has been simplified in ways that may or may not preserve the key physics. Both the measurement and the framework are uncertain at the same time. Managing that double uncertainty is one of the key challenges the field is working to address. It requires a different style of experimental reporting than physics has traditionally used. Not just, here is the signal we saw and here is what we think it means, but also, here is the model we were using. Here is how we know the simplification preserved the essential physics. Here is the range of parameters over which we verified the correspondence. Here are the checks we ran. And here are the limits of what we can actually claim. The wormhole paper, in retrospect, was not written in that style. It was written in a style that treated the holographic interpretation as established rather than as a claim to be tested. The 5 gravitational fingerprints were presented as evidence for the interpretation rather than as outputs to be independently verified against the requirements of the interpretation. The Berkeley group found the gap between those two modes of presentation, and the gap was significant. Let's return to the false vacuum experiment, because it illustrates the same underlying issue from a different angle. And because the physics it's probing is genuinely extraordinary, the idea of a false vacuum is one of the stranger implications of quantum field theory. In classical physics, vacuum just means empty space. In quantum field theory, vacuum means the lowest energy state of a quantum field. And the lowest energy state of a quantum field is not nothing. It's a specific quantum state with specific properties. Different fields can have different vacuum states. The Higgs field, which gives particles their mass through the Higgs mechanism, has a vacuum state where the field takes on a specific non-zero value throughout all of space. That vacuum expectation value is what breaks the electroweak symmetry and gives the W and Z bosons their masses. Now here's the question. Is the Higgs field currently sitting in its absolute lowest energy state? Or is it sitting in a local minimum, a valley that's not quite the deepest valley, with a lower energy configuration available if only the field could tunnel through the intervening energy barrier? The answer depends on the value of the Higgs boson mass and the mass of the top quark, both of which can be measured. When you use the measured values to calculate the shape of the Higgs potential, what you find is that the current vacuum state sits in a region that is technically the field is in a local minimum, but the global minimum of the potential appears to be at a much lower value of the field. A bubble of true vacuum, if it ever knew, would have the Higgs field sitting at a much lower value inside the bubble than it does in our current vacuum. The electroweak scale, the energy scale at which the Higgs mechanism operates, is roughly 246 billion electron volts. The scale of the true vacuum, if the metastability calculations are right, would be many orders of magnitude higher in energy, somewhere around 10 to the power of 11 billion electron volts, which is far beyond anything the Large Hadron Collider can probe directly. This means the barrier between our false vacuum and the true vacuum is extremely large in energy terms, and tunneling through it is correspondingly rare. The rough estimate for the vacuum lifetime, the expected time before a bubble spontaneously nucleates anywhere in our observable universe, is longer than 10 to the power of 100 years in some calculations. The current age of the universe is roughly 14 billion years, or about 10 to the power of 10 years. So the estimated vacuum lifetime is many, many times longer than the current age of the universe. By some estimates, It's longer than the time it would take all the black holes in the observable universe to evaporate through Hawking radiation, which is itself an inconceivably long time. But these calculations have enormous uncertainties. The estimate of the vacuum lifetime depends sensitively on the precise values of the Higgs boson mass and the top quark mass, and those measurements have experimental uncertainties. Small changes in those measured values can shift the vacuum lifetime by many orders of magnitude. The current measurements sit close to the boundary between stability and metastability. The uncertainty bands on the measured masses straddle the phase diagram in ways that make it genuinely unclear whether the electroweak vacuum is stable, metastable, or even technically unstable. This uncertainty is not a technical detail. It's a fundamental question about the nature of the ground state of our universe. If the vacuum is truly stable, the universe can last forever in its current form, at least until much later processes like proton decay and black hole evaporation reduce it to its final equilibrium state. If the vacuum is metastable, there's a non-zero probability per unit spacetime volume of a bubble forming somewhere in the universe at any moment. The probability is so small that it almost certainly hasn't happened yet, and almost certainly won't happen for an extraordinarily long time. But it's not zero. And there's one more uncomfortable wrinkle. The calculation of vacuum stability assumes that the standard model of particle physics is exactly right, with no new physics at any energy scale. If there are new particles or new forces beyond the standard model, they could, in principle, modify the Higgs potential in ways that either stabilize the vacuum or destabilize it further. We don't know. The Large Hadron Collider has found no evidence of new physics beyond the standard model at the energy scales it can probe, but that doesn't mean there isn't any. It just means it hasn't shown up yet. This is the backdrop against which the false vacuum simulation has to be understood. The researchers at Leeds, Jülich and Eister, weren't just running an interesting quantum simulation. They were building a laboratory version of a mechanism that might determine whether our universe is permanent or merely long-lived. The scale difference between the simulation and the real problem is enormous. 5,564 qubits arranged in a ring is not the same as the quantum field that fills three-dimensional space across the entire observable universe. One dimension is not the same as three. A microsecond coherence time is not a cosmological timescale, but the mechanism is the same. Quantum tunneling from a metastable state to a lower energy state, bubble nucleation, coherent growth, expansion, collision. The dimensionality and the scale are different, but the physics of the transition is governed by the same equations. Watching it happen in a controlled quantum system for the first time gives theorists a way to check their calculations against an actual measurement. The theory predicts where bubbles should nucleate and how fast they should grow. The experiment shows where they do nucleate and how fast they do grow. The comparison is the science. What the team found was that the theory was right. The predictions of quantum field theory in one dimension matched the behavior of the qubits. The distribution of bubble nucleation sites, the growth rates, the collision dynamics, all matched. That's a genuine experimental result. It's not a claim about our universe's vacuum stability, but it's a check on the theoretical machinery that would be used to make such claims. In a regime where that machinery can actually be tested, the fact that nobody challenged this experiment the way the wormhole experiment was challenged is itself informative. The Ising model is well understood. The behavior of a quantum annealer running an Ising model is comparatively well characterized. The mapping from the physical qubit dynamics to the mathematical model of false vacuum decay is cleaner and more direct than the mapping from the sparsified SIC model to holographic quantum gravity. This difference points at something important about the current state of Quantum simulation as an experimental method. Not all quantum simulations are equally difficult to validate. Some systems are well understood enough that a quantum simulation of them can be checked against multiple independent lines of evidence, classical limits in certain parameter regimes, exact solutions for small system sizes, symmetry arguments, comparison with related systems that have been studied by other methods. The false vacuum simulation fits into this category. It's a hard simulation, but it's a simulation of a system that theorists understand well enough to make precise predictions about. The holographic gravity simulation is different. The holographic correspondence, in the form relevant to the SYK wormhole experiment, doesn't have a clean classical limit you can check against. The mapping from quantum information to gravity is itself a non-trivial theoretical step. The sparsification adds another layer of theoretical uncertainty. The result is a chain of theoretical interpretations, each carrying its own uncertainty, and the final claim that the experiment showed gravitational behavior sits at the end of a long chain where each link needs to be independently justified. That's not impossible. Theoretical physics regularly makes predictions through long chains of mathematical reasoning, and experiments regularly test those predictions. But when the chain is long and the links are not all equally solid, the experimental result needs to be more than a single piece of data that can be fit to the hypothesis. It needs to be a result that's hard to fit to alternative hypotheses, a result that's specifically inconsistent with the non-interpretation and specifically consistent with the gravitational one. The Berkeley group showed that the most important piece of evidence the Jafaris team had offered for the gravitational interpretation, the perfect size winding signature, was in fact equally consistent with the non-gravitational interpretation. In fact, it was a prediction of the non-gravitational interpretation. That's a much stronger result than just casting doubt. It's showing that the evidence pointed the wrong direction. There is a productive way to read the history of this experiment and its aftermath. The original paper was ambitious, rigorous in its own terms, and genuinely novel. Nobody had ever run an experiment like this before. The team worked out a sophisticated theoretical framework, reduced it to something runnable on real hardware, ran it, and reported a result that matched their theoretical expectations. That's good science. The Berkeley critique found a flaw in the theoretical framework. That's also good science. The formal matters arising exchange gave both groups the opportunity to put their arguments on the record. That's the error correction mechanism of science doing what it's supposed to do. The uncomfortable part is the timeline. The paper was published in December 2022. The Berkeley critique appeared on Arxiv in February 2023. The formal matters arising response was published in Nature in July 2025. 2.5 years between the publication of the claim and the formal publication of the serious challenge. During those 2.5 years, the claim that physicists had built a traversable wormhole on a quantum chip circulated in public discourse, was cited in educational materials, appeared in review articles, and shaped how the field talked about the prospects for quantum simulation of gravity. The mechanism that corrected the error worked, but it worked slowly. And the question of whether it would have worked at all, if the claim had been less dramatic and less visible, is worth sitting with. There is a long history in physics of experiments that were reported correctly in their technical details, but whose interpretation was contested for years or decades afterward. The discovery of the positron in 1932 by Carl Anderson is a clear example of an experiment where the data was correct and the interpretation was radical. The interpretation was right in that case, and the positron is now a standard part of the particle physics toolkit. The early history of the detection of gravitational waves is a different kind of example. Joseph Weber, who built the first gravitational wave detectors in the 1960s, reported detections that other groups couldn't replicate. The interpretive claims didn't hold up, even though the experimental work was genuine and innovative. The pattern that shows up in these historical cases is that new experimental technologies, when they're powerful enough to probe genuinely unprecedented regimes, tend to produce results faster than the community can critically evaluate them. The detectors are so sensitive that any output looks potentially real. The theoretical frameworks for interpreting the output are not fully worked out. The incentives are to publish striking results quickly. The machinery for careful validation is underdeveloped because nobody has needed it. Before quantum simulation is in exactly this position. The devices are powerful enough to do things no classical computer can do. The theoretical frameworks for interpreting the results are still being worked out. The incentives in modern academic physics, shaped by funding structures, journal prestige, and public attention, push toward dramatic claims. The tools for validation are years behind the tools for computation. This isn't a criticism of any individual physicist or any individual group. It's a structural feature of a field in a particular phase of development. The wormhole experiment was done by excellent physicists using the best available hardware, working from a genuinely sophisticated theoretical framework, and reporting results that matched their theoretical expectations. The Berkeley critique was done by equally excellent physicists who read the paper carefully and found a problem that the original team had missed. The Swinburne validation work was done by physicists tackling the general problem of quantum simulation verification without reference to any specific experiment. None of these groups made mistakes, in the sense of being careless or dishonest. The system worked, eventually. The question is whether it will scale. As quantum computers get larger and more powerful, the simulations they can run will get further from anything a classical computer can check. The experiments will be harder to evaluate. The theoretical frameworks needed to interpret them will be more complex. The gap between publishing results and validating them will grow, unless the field develops better tools and better norms for managing that gap. The tools are being developed. Classical simulation techniques are improving, which helps verify quantum simulations in regimes where the two overlap. Error mitigation and error correction techniques are advancing, which helps distinguish genuine quantum computation from hardware noise. New theoretical methods for checking holographic correspondence in specific models are being developed. The community is aware of the problem. The norms are changing more slowly. Scientific culture is conservative, and for good reasons. Norms that have worked well for a long time don't change quickly. The norm of reporting a striking result and letting the community evaluate it over time has worked well in most of physics for most of its history. It may need modification for quantum simulation in a way that hasn't fully happened yet. Consider the question of what it would take to convincingly demonstrate quantum gravity in the laboratory. Not in a toy model, not in a sparsified proxy, but in a genuine holographic correspondence between a quantum system in a lab and a gravitational system with real black holes and real spacetime geometry. What would that look like? The most straightforward answer is, you would need a quantum computer large enough to run a faithful version of the SYK model without the sparsification step. Not 7 Majorana fermions with a handful of interaction terms, but hundreds of Majorana fermions with the full set of random interactions. A system that genuinely saturates the chaos bound across all its degrees of freedom, not just in a simplified proxy. That would eliminate the ambiguity about whether the gravitational behavior is real or an artifact of the simplification. How many qubits would that take? The full SYK model with n Majorana fermions requires a Hilbert space of dimension 2 to the power of n over 2. For n equals 100, that's a Hilbert space of dimension roughly 10 to the power of 15. Running a faithful quantum simulation of that system would require something in the range of 50 to 100 logical qubits with full fault-tolerant quantum error correction. The best current quantum computers have hundreds of physical qubits, but only a handful of logical qubits. Because many physical qubits are needed to encode and protect each logical qubit from errors, the leading estimates for when fault-tolerant quantum computers with hundreds of logical qubits might become available range from the early 2030s to the mid-2030s. Some optimistic projections put the timeline shorter. Some more conservative projections extend it further. But the broad consensus is that the hardware is improving on a trajectory that will eventually make that scale reachable. When that scale is reached, the wormhole experiment and its controversy will look different. The argument about whether the sparsified model was genuinely holographic will be replaced by an experiment running on a system that is unambiguously holographic by construction. The teleportation signal will be a result from a genuine traversable wormhole analog, not from a commuting proxy. The gravitational fingerprints will either be present or they won't, and in either case the answer will be informative. That future experiment might confirm that the original interpretation was essentially right, that the sparsified model captured enough of the holographic structure to produce genuinely gravitational teleportation, even if it wasn't perfect. Or it might confirm that the Berkeley critique was right, that genuine holographic behavior requires the full non-commuting chaos of the SYK model, and that no shortcut through sparsification can substitute for it. Either result will be valuable. Meanwhile, the false vacuum program is moving in its own direction. The Leeds Jülich ISTA team's one-dimensional simulation is explicitly a stepping stone toward three-dimensional simulations. The path involves larger quantum annealers, with qubits arranged in two-dimensional and eventually three-dimensional lattice structures, running the simulation with progressively more spatial dimensions. Each additional dimension brings the simulation closer to the geometry of our actual universe and further from the regime where classical computers can check the results. The physics question those simulations. Our targeting is whether quantum fluctuations in the early universe could have seeded a population of true vacuum bubbles that grew and collided, and whether that process left any observable signature in the cosmic microwave background, the distribution of galaxies, or the properties of gravitational waves. The current measurements don't show any clear evidence of false vacuum decay in the early universe, but the theoretical predictions of what such signatures would look like depend on calculations that are extremely difficult to do analytically. Quantum simulation could make those calculations tractable. There's a third frontier worth following, one that doesn't get as much attention as wormholes or vacuum decay, but that may ultimately be more foundational. It's the question of what entropy means in quantum gravity. Black holes have entropy. The entropy of a black hole, calculated by Jacob Bekenstein and Stephen Hawking in the 1970s, is proportional to the area of the event horizon, not the volume of the region inside. This is deeply strange. For ordinary systems, entropy is an extensive quantity, meaning it scales with the volume of the system. A gas in a box has entropy proportional to the volume of the box, but a black hole's entropy scales with the surface area of the horizon, not with the volume of the black hole's interior. This area scaling is one of the key observations that led to the holographic principle. The information content of any region of spacetime is bounded not by the volume of that region, but by the area of its boundary. This is the Bekenstein-Hooft bound, sometimes called the holographic entropy bound. It means that spacetime cannot contain arbitrarily large amounts of quantum information per unit volume. The density of information is bounded by the surface through which it can be accessed. When Maldacena worked out ADS One of the first and most important checks on the correspondence was that it correctly reproduced the entropy of black holes. The entropy of the gravitational black hole, calculated from the area of the event horizon, matched the entropy of the corresponding quantum field theory state, calculated through standard quantum mechanical methods. That match was not a coincidence. It was a confirmation that the correspondence was capturing the right physics. Hawking radiation, which is the thermal radiation that quantum mechanics predicts should be emitted by black holes, carries this entropy puzzle to its sharpest point. A black hole that evaporates through Hawking radiation starts with a large amount of entropy, which should be carried in the information content of the matter that fell in. As the black hole evaporates, the information should eventually come back out in the Hawking radiation. But Hawking's original calculation suggested that the radiation was exactly thermal, containing no information about what had fallen in. That would mean the information was destroyed. But destroying information is forbidden by quantum mechanics. This is the black hole information paradox. The holographic correspondence suggests a resolution. Because the black hole is dual to a quantum system in flat space, and quantum mechanics preserves information, the information must come back out in the Hawking radiation, even if we can't easily track it. The ADS-CFT correspondence essentially guarantees that black hole evaporation is unitary, meaning information preserving, because it maps to a unitary quantum mechanical process on the other side of the holographic dictionary. But working out the details of exactly how the information comes back out, and what it implies about the semi-classical geometry of the evaporating black hole, is still an active research program. In recent years, this program has produced some surprising results, including the discovery that the geometric path integral over certain quantum gravity configurations, called replica wormhole, appears to correctly reproduce the expected behavior of the information content of Hawking radiation as a function of time. This result, worked out by Ahmed Almhiri, Netta Engelhardt, David Marolf, Henry Maxfield, and others, has been called a significant step toward understanding the black hole information paradox. Quantum simulation could eventually play a role in testing these ideas as well. If you can build a quantum system that is holographically dual to an evaporating black hole, and if you can run that system long enough to observe the information come back out in the analog of Hawking radiation, you could test the replica wormhole calculation directly. That's a much more demanding experiment than anything currently possible, but it's on the same conceptual roadmap as the wormhole experiment. The common thread running through all of these research programs is the use of quantum information theory to understand gravity, not just as a tool for calculating things that were previously intractable, but as a language for expressing what gravity fundamentally is. The holographic principle suggests that gravity is not a fundamental force in the same sense that electromagnetism and the nuclear forces are. It might be an emergent phenomenon arising from the entanglement structure of a quantum system on the boundary of spacetime. If that's right, then understanding quantum information is not just useful for studying gravity, it is how you study gravity. That's a radical idea. It's not proven. The holographic correspondence is a precise mathematical duality for specific spacetimes, not a derivation of gravity from quantum information in general. Extending it to our actual universe, with its de Sitter geometry and its observed cosmological constant, is a major unsolved problem. The connection between bulk, spacetime geometry, and boundary entanglement is still being worked out in detail. Tensor networks, which are mathematical structures that encode entanglement in a spatial pattern, have been proposed as toy models for how spacetime geometry might emerge from entanglement. But making those models precise and testable is ongoing work. What we can say with confidence is that the connection between quantum information and gravity is deep and real. It shows up in the black hole entropy formula. It shows up in the holographic entropy bound. It shows up in the black hole information paradox. It shows up in the ADS-CFT correspondence. It shows up in the area law for entanglement, entropy in quantum field theories, which mirrors the area law for black hole entropy. These are not isolated coincidences. They are converging arrows pointing at a relationship that runs through the deepest structure of both theories. The experiments being done with quantum computers are attempts to make that relationship tangible, to build something in a laboratory that manifests the holographic dictionary as a physical phenomenon, not just a mathematical correspondence, to watch information behave the way it would if space-time geometry were real. Whether any specific experiment has achieved that goal is a question the field is still arguing about. Whether the 9-qubit wormhole signal was gravitational or commutative, whether the sparsified SYK model preserved enough holographic structure to count, whether the 5000 qubit vacuum simulation tells us something about our universe's ground state or just about one-dimensional Ising models at low temperature. These arguments are not weaknesses of the field. They are the field working. The same process that produced the Berkeley critique will produce the next generation of better experiments. The same uncertainty that surrounds the wormhole. Interpretation motivates the development of validation, tools that will make the next generation of quantum gravity experiments more reliable. The path from a 9-qubit processor in a dilution refrigerator to a genuine laboratory test of quantum gravity is long. It passes through fault-tolerant quantum computing, through better understanding of holographic models in various regimes, through improved techniques for quantum simulation validation, and through theoretical advances in connecting holography to realistic cosmological spacetimes. But it is a path, and people are walking it. That is new. For most of the history of quantum gravity research, the field was purely theoretical. There was no experimental input. There couldn't be. The energies at which quantum gravitational effects become significant are far beyond any particle accelerator that exists or could plausibly be built. The only data came from thought experiments and mathematical consistency. Arguments that the advent of quantum simulation has changed that, not by giving us access to quantum gravitational energy scales. That gap is still vast, but by giving us access to systems that are holographically dual to gravity, that can exhibit the signatures of gravitational behavior through the dictionary of the correspondence, and that can be controlled and measured in a laboratory. This is not the same as directly observing quantum gravity. It is, possibly, the next best thing. A window into gravitational physics through a side door that nobody realized was there until Maldacena pointed it out, and that nobody could actually open until quantum computers became sophisticated enough to run the right models. The window is open now. The view through it is blurry. Some of what we think we see might not be there, but the window is real. The view is improving, and the physics on the other side of it is among the deepest and most fundamental there is. Let's take a step back and think about the broader implications of what's happening here. Because the quantum simulation program isn't just changing physics, it's changing what kind of evidence we can have about fundamental reality. And that's a shift worth examining carefully. For most of the history of science, experimental evidence came in two forms: direct measurement, where you build an apparatus that interacts with the phenomenon you want to study and you read off the result, and indirect measurement, where you observe the effects of something you can't directly access and infer its properties from those effects. We can't directly observe an electron's wave function, but we can build a double-slit apparatus and observe the interference pattern that results from it. We can't directly observe a quark inside a proton, but we can fire electrons at protons at high energy and observe how they scatter. The inference from observation to underlying reality is always theory-mediated, but for most of the history of physics, that mediation has been well enough understood that the inference was solid. Quantum simulation introduces a new mode of evidence. You're not directly measuring the system you're interested in. You're building a different system that is theoretically equivalent to the system you're interested in, and you're measuring that proxy system instead. The evidence about the target system is mediated not just by a theory about how to interpret measurements, but also by a theory about the equivalence between the proxy system and the target system. This is actually not new in all respects. Computer simulation has been used as a proxy for experimental evidence for decades. Climate models, molecular dynamics, simulations, and lattice quantum chromodynamics. Calculations all use classical computers to simulate systems that are too complex to solve analytically. The outputs of those simulations are used to make predictions about physical systems and are compared against observations. The simulations are taken seriously as evidence, but quantum simulation is different in a crucial way. Classical simulations can, in principle, be verified. You can check the code. You can run test cases where the answer is known. You can compare against independent calculations. The simulation is just mathematics, and mathematics is transparent. Quantum simulation is not transparent in the same way. The calculation happens in the quantum state of the hardware, in the correlations between thousands of entangled qubits, and there is no efficient way to extract and examine the full state without destroying it. This opacity is a fundamental feature, not a bug. It's the same feature that makes quantum computers powerful. The quantum state encodes exponentially more information than a classical description of the same system. You can't extract all of that information efficiently, but it means you also can't fully check whether the calculation is doing what you think it's doing. The theoretical physicist John Bell, famous for Bell's theorem and Bell inequalities, once said that the most important word in science is not truth or proof, but rather the word correlate. What is it that we know? And what is it that we've actually measured? And how do we know those two things are correlated? The verification problem in quantum simulation is really a sharpening of that question. We have a signal. We have a theory. What correlates the signal to the physical reality the theory describes? And how certain are we that the correlation holds? For the wormhole experiment, the correlation was mediated by the holographic dictionary, which is a precise mathematical correspondence, and by the sparsification process, which introduced uncertainty. The Berkeley group found that the sparsification had broken the correlation in a way the original team hadn't noticed. The dictionary was right, but the system being translated through the dictionary wasn't the system the team thought it was. For the false vacuum simulation, the correlation is more direct. The physics of the Ising model is well understood. The mapping from Ising model dynamics to false vacuum bubble nucleation is theoretically clean. The correlation holds. In the regime, the experiment was done, but it holds for one-dimensional dynamics only. The correlation between the one-dimensional simulation and three-dimensional false vacuum dynamics in our actual universe is a theoretical extrapolation, not a direct correspondence. In both cases, the experiment gives you something real data from a real quantum system. What you do with that data depends on the quality of the theoretical bridge connecting the quantum system to the physical phenomenon you care about building. Better theoretical bridges is therefore as important as building better quantum hardware. And this is where a somewhat different research tradition becomes relevant. The tradition of rigorous mathematical physics, where the goal is not just to compute things, but to prove things. to establish mathematically rigorous bounds on when a quantum simulation faithfully represents its target system and when it doesn't. The mathematical physics community has known for a long time that the SYK model is a challenging system to work with rigorously. The randomness in the interaction strengths makes it hard to make precise statements about all realizations of the model, as opposed to statements that hold on average. The large n limit, where n is the number of fermions and you take it to infinity, is where the holographic behavior is cleanest, and that limit is far from any experimentally realizable system. Connecting the behavior of a finite n sparsified system to the large n holographic limit requires theoretical estimates that may or may not be reliable. The broader program of using machine learning to find simplified models that preserve key physical properties is both powerful and risky. Powerful because it can find simplifications that human intuition might miss. Risky because machine learning algorithms optimize for the objectives they're given, and it's not always clear that the objectives capture everything that matters. The algorithm that sparsified the SYK model was optimizing for certain measures of similarity to the full model. It found a simplified model that was similar in those respects, but the commutativity issue was a different kind of property, one that the optimization wasn't explicitly checking for, and the simplified model had it without anyone noticing. This points to the need for a more comprehensive checklist of what properties a quantum simulation must preserve in order to be considered faithful to its target system, not just scrambling rate, not just teleportation fidelity, but also the algebraic structure of the operators, the distribution of eigenvalues, the behavior under various perturbations, the response to symmetry operations, and other properties that may seem secondary but turn out to be essential. Developing such a checklist and developing the theoretical tools to verify that a given quantum simulation satisfies it is a real research program. Several groups around the world are working on it. The output of that work will look less glamorous than a wormhole experiment. It will be a series of papers establishing rigorous bounds and proving theorems about quantum simulation fidelity, but its foundational work and the striking experiments that rely on quantum simulation will only be as trustworthy as the foundations they rest on. This brings us to the question of the future of the field, not in the abstract sense of where might this eventually lead, but in the concrete sense of what are the most important experiments and theoretical results that physicists are actually working toward right now. On the holographic gravity side, several groups are working on larger versions of the SYK experiment, using more qubits and less aggressive sparsification to test whether the gravitational signatures become more robust as the system size increases. If the commuting Hamiltonian issue was the key problem, then a larger, less sparsified system should show clearer gravitational behavior. If the behavior doesn't become more robust as the system size increases, that would suggest the issue runs deeper than the simplification. Several groups are also working on different holographic models, not just SYK, but other systems that are known to be holographically dual to gravitational theories. The advantage of working with multiple models is that if they all show the same gravitational signatures, it's harder to dismiss the signatures as artifacts of one specific model's unusual properties. If they show different signatures in ways that are consistent with their different holographic duals, that would be strong evidence that the holographic dictionary is real. On the vacuum stability side, the trajectory toward three-dimensional simulations is the main frontier. The technical challenge is that a two-dimensional or three-dimensional Ising model on a quantum annealer requires qubits to be connected in a lattice with specific coupling patterns. D-Wave's most recent quantum annealers have Pegasus and Zephyr, topology graphs that allow for certain connectivity patterns, but not others. mapping a two-dimensional false vacuum simulation onto available quantum hardware requires clever, graph-embedding techniques that introduce their own theoretical uncertainties. Groups at several universities and national laboratories are actively working on this mapping problem. On the quantum simulation verification side, the Swinburne result represents one direction of development, using the mathematical structure of specific types of quantum computation to derive testable predictions about what the output should look like in the absence of errors. A more general approach, which is currently the subject of significant theoretical work, involves the concept of quantum simulation certification, where you design the simulation from the start with built-in verification checks, running the simulation in parameter regimes where the answer is known, alongside the main simulation in the regime you actually care about, the longer-term frontier, which is probably at least a decade away, is fault-tolerant quantum simulation. Current quantum computers are noisy. The qubits make errors. The gates have finite fidelity. Error mitigation techniques can partially compensate for these errors, but they can't eliminate them. Fault-tolerant quantum computers, which use quantum error correction to protect logical qubits from physical errors at the cost of using many more physical qubits, would allow quantum simulations to run without accumulating errors over time, enabling much deeper circuits and much longer coherence times. Fault-tolerant quantum computing at a useful scale, with enough logical qubits to run a full unfalsified SYK model or a three-dimensional false vacuum simulation, is the enabling technology for the next generation of quantum gravity experiments. The timeline is uncertain, but the roadmap is clear. What will the field look like when that technology is available? The honest answer is that nobody knows. The history of quantum mechanics itself is a cautionary tale about the difficulty of predicting what a new experimental technology will reveal. When Paul Dirac worked out the relativistic quantum mechanics of the electron in 1928, he found that the mathematics required a particle with the same mass as the electron but opposite charge. He initially doubted whether such a particle could be real. 2 years later, Carl Anderson found the positron in cosmic ray tracks. The mathematics had told the truth. Quantum simulation of holographic gravity might work the same way. The mathematics of the holographic correspondence might be telling us something real about the structure of spacetime, something that quantum simulation experiments will eventually confirm in a way that's impossible to dismiss. Or the mathematics might be a precise correspondence that holds in specific settings but doesn't generalize to our actual universe in the way everyone hopes. The experiments won't answer that question definitively, at least not for a long time, but they'll constrain the answers. They'll tell us which specific predictions of the holographic framework are true and which aren't. In the regimes that are experimentally accessible, that's how science works. Not through single experiments that settle everything, but through a progressive narrowing of the space of what's possible. The physicists running these experiments know this. The goal is not to prove that spacetime is holographic in a single paper. The goal is to probe the holographic dictionary in a regime that has never been probed before, to find out what it actually predicts and to compare those predictions against reality. That's a program that will take years or decades and involve hundreds of experiments and thousands of theoretical papers. It's happening now, imperfectly, with the controversy and the validation problems and the gap between experimental claims and what the data actually supports. But it's happening. If you find this kind of work genuinely fascinating, if the intersection of quantum computers, gravitational physics, and the deep structure of space-time is something you want to keep following, then subscribing so that you see future videos is the best way to stay with it as the story develops. The next few years are going to produce results that matter, some of them dramatic and some of them quietly transformative. This is physics at one of its genuine frontiers. The 9 qubits in Santa Barbara. The 5,564 qubits in the next machine, whatever it is and wherever it runs, with more qubits and better error correction and sharper theoretical frameworks, each one asking the universe a question it has never been asked from inside a laboratory. Some of what we hear back will be real, some will be artifact. Learning which is which, with the rigor the question deserves, is the work of the next era of experimental physics. It's slow work and careful work, and occasionally the headlines get ahead of the facts. But the questions are genuine, the tools are improving, and the universe is not obviously refusing to answer. There's one more dimension of this story that hasn't been addressed yet, and it sits at the boundary between physics and philosophy. The question of what it actually means for a quantum computer to simulate a physical system. When physicists say a quantum processor simulated a wormhole or simulated false vacuum decay, they are using the word simulate in a very specific technical sense that is different from the everyday meaning. In everyday usage, a simulation is a model, an approximation, a stand-in. A flight simulator doesn't actually fly. A climate model doesn't actually have an atmosphere. The simulation represents something real without being that thing. In quantum simulation, the situation is more subtle. The quantum system running on the processor is real. The qubits are real physical objects. The quantum states therein are genuine quantum states. The entanglement between them is genuine entanglement. The measurements made on them are real measurements, producing real data. The thing happening inside the quantum computer is not a representation of physics. It is physics. The question is whether the physics happening inside the quantum computer is the same physics as the physical system being targeted. And that's a question about mathematical correspondence, about whether the Hamiltonians are the same, about whether the degrees of freedom map onto each other in the right way, about whether the observable quantities correspond. This distinction matters because it changes what kind of knowledge a quantum simulation can provide. A classical simulation of a physical system can tell you what the mathematics predicts, but you still have to trust that the mathematics is correct. A quantum simulation of an equivalent physical system can tell you what the physics actually does, because you're not running the mathematics, you're running the physics. If the quantum system is truly equivalent to the system you're studying, the simulation isn't an approximation. It's the real thing, just in a more accessible form. This is Richard Feynman's original idea. In a famous 1982 talk, Feynman pointed out that simulating quantum mechanics on a classical computer is exponentially hard, because the state space of a quantum system grows exponentially with the number of particles. A classical computer trying to simulate a system of 100 quantum particles would need to track 2 to the power of 100 amplitudes, which is far beyond any classical computer that exists or could exist. But a quantum system of 100 quantum particles simulates itself perfectly and efficiently, simply by existing. The idea of quantum simulation is to use a controllable quantum system to do the simulation that a classical computer can't. If that program works as intended, then a quantum simulation of a traversable wormhole isn't a model of a wormhole. It's a wormhole. Not in our spacetime, not in any spacetime you could visit or observe directly, but in the holographic dual space that is physically real and mathematically identical to the spacetime described by the gravitational theory. The qubit that teleported through the 9-qubit processor didn't just model traversing a wormhole. If the holographic correspondence holds, it traversed a wormhole, in the only sense that matters physically. That's a remarkable claim. And it's the claim that the Berkeley critique put under pressure. If the Hamiltonian used in the experiment wasn't actually holographically dual to a gravitational system with a traversable wormhole, then the qubit didn't traverse a wormhole. It traversed a quantum circuit. Those are not the same thing. The word simulate, in the quantum context, is only as meaningful as the correspondence between the simulator and the target. When the correspondence is exact, simulation becomes realization. When the correspondence is approximate, or when it holds only in certain limits, the simulation is just a model like any other dot. This is a genuinely difficult conceptual issue, and it's not going to be resolved by any single experiment. It requires a careful theoretical characterization of exactly which physical quantities are preserved under the holographic dictionary and which are not. It requires understanding the limits of validity of the correspondence, the places where the quantum system and its gravitational dual behave differently, and it requires experiments designed to probe those limits, not just to confirm that the correspondence holds in the regime where everyone already knows it works. The wormhole experiment was an attempt to do exactly that. It aimed to probe the holographic correspondence in a regime, the regime of traversable wormholes and quantum teleportation that nobody had ever been able to reach in a controlled laboratory setting. The fact that the attempt ran into problems with the sparsification doesn't mean the aim was wrong. It means the tools weren't yet adequate to the ambition. The tools are improving. The theoretical understanding of what makes a quantum system genuinely holographic, as opposed to merely resembling a holographic system in some respects, is sharpening. The experimental capabilities are advancing. The verification methods are being developed. The questions at the heart of this program, about the relationship between quantum information and spacetime, about whether the universe we live in is fundamentally holographic, about whether our vacuum is stable or about what happens to information when it falls into a black hole, are not questions that will be answered in a single paper or a single experiment. They are questions that will be answered, if they are answered, through a long accumulation of experimental results and theoretical advances, each one moving the boundary of what is known a small step further. That process is underway. It is producing controversies, because genuine progress at the frontier always does. It is producing corrections to previous claims, because that is what careful science looks like when it is working. It is producing better experiments, better theories, and better tools for connecting the two. The 9 qubits were a beginning, not the end.